If we model probability by subsets of a set or subregions of a region in the plane, then all of the properties of subsets and subregions that we talked about in lesson 2 translate immediately into probability. So let's look at what those statements look like in terms of probability. So let's let S be a sample space, which is either a finite set or a region in the plane. Let's let A and B be events, that is, subsets of S, which could be finite or if S is infinite, subregions of S in the plane. So the probability of A is either number of elements in A over number of elements in S, if S is finite, or area of A over area of S, if S is a region in the plane. So fact 1, the probability of A is somewhere between 0 and 1, as it should be. And the reason is we have the empty set inside of A, which is inside of S. If S is finite, then this means that 0 is less than or equal to the number of elements in A, which is less than or equal to the number of elements in S. Then we can divide by cardinality of S to get 0 over cardinality S is 0. Cardinality of A over cardinality of S is probability of A. Probability of S, cardinality of S over cardinality of S is 1. Just as we wanted. That's if S is finite. If S is a region in the plane, then this set containment here means that the area of the empty set of the plane, which is 0, is less than or equal to the area of A, which is less than or equal to the area of S. Now we divide by the area of S. To get 0 over area of S is 0, less than or equal to area of A over area of S is probability of A. And then area of S over area of S, of course, is 1. So that proves fact 1. Fact 2, the probability of S is 1. Well, we sort of did this already because it's on the right-hand side of these inequalities. The reason, again, is if S is finite, then probability of S equals number of elements in S over number of elements in S, which is 1. If S is a region in the plane, then probability of S is area of S over area of S, which is 1. Fact 3. The probability of A union B equals probability of A plus probability of B minus probability of A intersect B. In particular, it's just probability of A plus probability of B if A and B can't happen simultaneously. The reason is, so first of all, for S finite, we know that the cardinality of A union B, that is the number of elements in the set A union B, is number of elements in A plus number of elements in B minus the number of elements in the intersection. So we divide by cardinality of S to get number of elements in A union B over number of elements in S equals number of elements in A over number of elements in S plus number of elements in B over number of elements in S minus number of elements in the intersection over number of elements in S. And this is probability of A union B, and this is probability of A, this is probability of B, and this is probability of A intersect B, that is A and B both happening. So A and B happen simultaneously there. If A and B can't happen simultaneously, we just get probability of A plus probability of B. Now for S, a region in the plane, we have a similar equality. The area of A union B equals the area of A plus the area of B minus the area of A intersect B. And then we divide by area of S to get, well, area of A union B over area of S is probability of A union B area of A over area of S is probability of A. Area of B over area of S is probability of B. And area of A intersect B over area of S is probability of A intersect B. Again, if A and B can't happen simultaneously, that is, those two subregions don't intersect, then we can just forget about this. This is 0 if A intersect B is empty. And then we can just stop here. All right, fact 4. The probability of A complement is 1 minus probability of A. And the reason is whether S is finite or not. The whole point of A complement is that S is A union A complement, and A intersect A complement is the empty set. Now, if S is a finite set, we can divide by number of elements in S to get, well, before we divide, I guess we can write this in terms of just cardinalities. So since S is equal to the union, cardinality of S is equal to the cardinality of the union. But we know that the cardinality of a union of sets by fact 3 equals cardinality of the first plus cardinality of the second minus cardinality of the intersection. Now A and A complement don't intersect. So this is just cardinality of A plus cardinality of A complement. Now let's divide by cardinality of S to get cardinality of S over cardinality of S, which is 1, equals cardinality of A over cardinality of S plus cardinality of A complement over S. And this is probability of A, and this is probability of A complement. So 1 equals probability of A plus probability of A complement, which is basically what this is saying. If we just add probability of A to both sides, that's exactly what it says. Alright, now what if S is a region in the plane? So we have the area of S equals the area of A plus the area of A complement minus the area of A intersect A complement. But this is empty, so that's just 0. Now we divide by the area of S to get area of S over area of S is 1 equals area of A over area of S this is probability of A plus area of A complement over area of S, and this is probability of A complement. So again, we have 1 equals the sum of these two probabilities, which is exactly what we're claiming in the fact. Fact 5. The probability of A1 union, let's say we have k different regions. Let's say n, so I'm consistent with the book. We have n different regions, and we take the probability of the union. This equals the sum of the probabilities of each one of those sets separately minus the sum over a pair's probability of A1 intersect AI1, AI2. So all pairs of these sets here, take the intersection, plus the sum over all triples of indices, probability of AI1 intersect AI2 intersect AI3, etc. And finally, we get to the probability of the intersection of all of these. A1 intersect A2, etc. up to AN. And the signs alternate, so we're going to end up with a -1 to the n plus 1 here. And the reason, I'm not going to write this all out 2 more times, is by the principle of inclusion and exclusion. This holds for set cardinalities and areas of regions in the plane. So that is the properties of probability, which follow from our properties of subsets and subregions of the plane. The end.